So we are going to continue to explore some of those equations related to gases and their behaviors. So let's start with a practice, a review problem. Calculate the pressure in atmospheres of 7 moles of carbon monoxide stored in a 30-liter container at 65 degrees Celsius. So I can recognize that this is what I would call a Pivnert problem, or a problem where I need to apply the ideal gas law. And you might be wondering, like, how do you know that? Well, there's a red flag that's given that I need to use the ideal gas law. So what is that red flag? So a problem that requires that you apply Pivnert or the ideal gas law is going to give you 3 of the 4 variables. So it's going to give you P, V, N, or T, so 3 of them, and ask you to solve for the missing one. So if you look at that problem, look for that red flag. So calculate the pressure. So it's asking me to find the pressure. That's the missing one. And it specifies in atmospheres, which is going to help me in deciding my R values, of 7 moles of carbon monoxide in a 30-liter, that's a volume, container at 65 degrees Celsius. So it meets that red flag. It's telling me there's my tip-off that I need to apply the gas law. So I'd encourage you to pause the video here, since we've already covered the ideal gas law, and work through that problem. So I'll give you a second to do that, and then you can check your work. So here is my working out of that. You can see all my various scribbles. I have the answer down here, reflecting hopefully the correct sig figs, and you can see how I've set up the problem. If in looking at that, you can pause the video and do a little bit of analyzing. If you still have questions on it, make sure to let me know, and I can try to help you walk through it. So let's look at another problem. What is the volume of a gas at 2 atmospheres if its original volume was 300 liters at 0.25 atmospheres? So hopefully you're kind of pausing for a second and going, wait a minute, that is not a Pivnert problem. That doesn't have that flag. In fact, it has 2 pressures in it. It gives me 2 different pressures. So this is a different kind of problem, which means we can't just use the ideal gas law. We can't just go, okay, P equals V, or, you know, we need a new gas law. So before we get to this problem itself, though, let's consider the following situation. So I'm going to do some color changing because I like to. So let's say I have a particular gas, and it is under situation 1, and I'm just gonna have a 1 here, situation 1. So here's my gas. It's in, maybe, let's say, a balloon. It's my extremely amazingly drawn balloon. And so in situation 1, with my gas at a particular volume and pressure and temperature, then I would assume that the ideal gas law would be true. So Pivnert would be true. PV equals nRT. Now, if I wanted to, could I solve for R in this equation? I know you might be thinking, why would I want to solve for R? It's a gas constant. But just bear with me for a second. Well, I could. If I wanted to solve for R, I would want to get N and T out of there. So divide them out, and they divide out. But what you do to one side, you have to do to the other. So, you know, that's, so by the time I'm done, I get R equals PV over NT. Now, let's say something about the situation with my gas changes. So so this is going to be situation 2. You know, I let in some more air, so you know, I have more N. The temperature of the room really goes up dramatically. Maybe the pressure changes. So I'm going to have this new situation. I'll draw my balloon a little bigger. You know, it's warmer. There's a lot going on. So situation 2. Now, Pivnert still can be used for situation 2, but you're going to see that the values of it aren't the same. Like I said, the pressure might have changed, the volume, you know, number of moles, temperature, any of those variables could change, but the ideal gas law is still true for those new situations. So could I still solve for R in my new situation? Of course. I could divide out NT on both sides. So they would divide out, they don't divide out over here, so I get R equals PV over NT. So I have situation 1 set equal to R and situation 2 equal to R. But what about these two values of R? It's a gas constant, right? The R value hasn't changed, even though these variables might have. Now, I know you might be thinking, like, if the variables change, R has to change. But think about all the different numbers that you can think of that when you multiply and divide them can get to 100. You know, you can take, 50 times 2, lots of different combinations that can get you to 100. So even though these combinations have changed, the R hasn't. And what did we learn, I don't know, a million years ago, back like in maybe middle school? I don't really remember when we learned this. When we have two equations that are both equal the same thing, we can set them equal to each other. So it's not that the pressure is the same as the pressure or the volume is the same. These values themselves aren't the same, but the pressure to volume, pressure times volume, the product of pressure times volume over NT, that ratio is the same. So I said situation 1, so the pressure in situation 1 times the volume in situation 1 divided by the number of moles in situation 1 times the temperature in situation 1 is going to be equal to that same ratio, but with the variables from situation 2. So what we're getting at here is a new law. It's called the combined gas law. And it looks like this. Now, one thing you'll notice if you look it up in your book or in several places on like the internet, you'll see there isn't an N here. And that's because the truth is the amount of moles doesn't change that often. But I actually really like including the N because, first of all, the amount of moles can change. You can lose gas particles. You could gain, more could be reacted. So I like having it in there. Plus, without having it in there, I don't quite recognize that this is how we calculate R. This is R equals R. It also helps me remember it. If I forget it, I can just derive it from R. So this is the combined gas law, or I call it the Star Wars law, because listen, if you say it really fast, P1 V1 over N1 T1 equals P2 V2 over N2 T2. So it's the Star Wars law. And we will use the combined gas law that looks at the different variables together when? How are we going to know? Well, there's a red flag for that too. We will recognize that we need to apply this gas law when you're asked to calculate a new gas property after a change. So in like our last problem, it said the pressure was this. At this volume, what's the new pressure? So let's go back to that problem. What is the volume of a gas at 2 atmospheres if its original volume was 300 liters at 1/4 of an atmosphere? So recognize that red flag there. See, it's telling you of a situation 1 and a change occurred, and what's the new trait at situation 2. So what is the volume of a gas at 2 atmospheres? If its original volume, so this was V1, originally it was V1 at this many atmospheres. So this is P1. So this is our new situation, new volume. So you can see that we've gone, oops, sorry, you gotta pay attention. This is P2. And it's asking me how much space is it going to take up now. So this is going to be my unknown that I'm going to solve for. Now you might be thinking, well, what about N and what about T? What about all of those other things? So the nice thing about the combined gas law is that if a variable doesn't change, if the temperature stays the same and the amount of moles stays the same, which is pretty typical, you can get rid of them. You can cancel them out completely. because they're going to divide out in the end anyway. So that's really nice because it simplifies our current problem to P1V1 equals P2V2. So now all I have to do is plug in those values. Go like, okay, pressure 1 was 0.250 atmospheres. And volume 1 was 300 liters. And the product of that should equal my unknown that I'm going to solve for times 2 atmospheres. So I'm going to end up dividing both sides by 2 atmospheres. So that divides out over there. Whoops. Sorry, guys. I like to keep my units because it helps me make sure I'm doing it right, because the ones I don't want should divide out and I should be left with the question, you know, the one that I'm interested in. So when I plug that into my calculator, I get 37.5. Yep, let me double check though. 37.5 liters. Sorry, that's an L. I always like to stop and ask myself on a question like this, does that make sense based on what I've learned about the gas laws? So you can see that the pressure went up really dramatically on this gas. It went from 1/4 of an atmosphere all the way up to twice the atmospheric pressure on Earth. So what did we learn in Boyle's law about volume when you increase pressure? Well, we learned that when you increase pressure, we would expect a decrease in volume because they're inversely related. So based on that, I can ask myself, does my answer make sense? Well, going from 300 down to 37 based on that dramatic increase of pressure does in fact make sense and reflects that the Boyle's law, which is actually this equation right there. Each of the individual gas laws can be derived from the combined gas law, which is why it's actually my favorite, because I feel like all of the gas laws are kind of embedded therein. So here is one more practice problem. I'm running out of video time, so I won't be able to work it out for you, but I can tell you, so that you can pause and then check your work, that in the end, you should get that the new pressure will be 1.71 atmospheres. So take a look at that and check your work. If you're unable to get to that solution, send me a Canvas message or email and I'll try to help you out. Good luck.